Welcome to Hart und Trocken. In this video, I want to introduce and discuss with you the so-called infinite geometric series. It is a special case of a sequence, and we want to understand under which circumstances this sequence has a limit and which value this limit has. Let us quickly recap the definition of a sequence from our last video. A sequence can be thought of as an assignment which assigns to every natural number n some real number an. It can be also thought as a function f mapping the natural numbers to real numbers. To denote a sequence, we typically write an in brackets followed by n element n. Of course, we can also use bn, cn or any other letter. A sequence can have a limit, that means a real number to which it tends when n goes to infinity. If a sequence has a limit, it is called a convergent sequence. Mathematically strictly speaking, the definition of a limit is the following. If for a sequence an a number g exists, such that for every interval around g, no matter how small the interval is, almost all members of the sequence are within the interval, then we call g the limit of the sequence. An equivalent, very condensed definition is this. Now let's talk about the main topic of this video, so-called infinite geometric series. An infinite geometric series is a special kind of a sequence. Instead of using an, which we typically use to denote a sequence, we use Sn to indicate that it's an infinite geometric series. Let's have a look at one special example for an infinite geometric series. The first member of the series, S0, equals 1. The second member of the series, S1, equals 1 plus 1/2. The third member of the series, S2, equals 1 plus 1/2 plus 1/4. And the fourth member of the series, S3, equals 1 plus 1/2 plus 1/4 plus 1/8. And so on. You see the principle. We can think of it as building a tower of bricks such that the first brick has the height 1, the second brick has the height 1/2, the third brick has the height 1/4, the fourth brick has the height 1/8, and so on. S0 is the height of the tower after one brick, S1 is the height of the tower after 2 bricks, S2 is the height of the tower after 3 bricks, and S3 is the height of the tower after 4 bricks, and so on. Now obviously, the principle of this infinite geometric series is to build longer and longer sums of increasing powers of 1/2. The nth member of the series, Sn, sums up all increasing powers of 1/2 until and including the nth power. If we write this using summation notation, we have sum over 1/2 to the power of I, where I is the summation index, and I runs from, well, it starts at 0 and it ends at n. So it runs from 0 to n. Now the question we want to discuss is what happens to Sn when n goes to infinity? Apparently, Sn is strictly monotonically increasing. So the question is if it is bounded and has a limit, or if it's unbounded and tends to plus infinity, where tending to plus infinity means that eventually it will get larger than any given natural number. Now looking at the illustration with the tower, the question is if the tower will grow infinitely high or if it will approach a finite limit. A likely candidate for a limit is the height of 2. So what do you think? Will the height of the tower stay below 2 for any given n, as large it might be, or will the tower grow infinitely high? Before we give an answer to this, we do another generalization step. We replace the number 1/2 by a general number q element r. Now we are ready to define a general infinite geometric series. For every real number q, we set Sn to be the sum of q to the power of k, where k runs from 0 to n. The question is now, what happens to Sn as n tends to infinity? In order to answer this question, we apply a little trick which allows us to rewrite the sum expression in an explicit form. That means we get rid of the summation. The first step is to write the sum in the expanded way. Now the trick is the following. We multiply this equation by q. The left-hand side turns into qsn, whereas on the right-hand side, each summand gets an extra factor q. Consequently, 1 turns into q, q turns into q squared turns into q to the third power, and so on. Finally, q to the power of n minus 1 turns into q to the power of n, and q to the power of n turns into q to the power of n plus 1. Now you see that by that shifting, the two right-hand sides are basically the same, except for 1 over here and q to the power of n plus 1 over there. Now we subtract the second equation from the first one. On the left-hand side, we have Sn minus Qsn, which is Sn times 1 minus Q. On the right-hand side, the respective pairs of corresponding powers cancel out, except for the ones in the blue boxes. So what remains is 1 minus Q to the power of n plus 1. If we now divide the resulting equation by 1 minus Q, we get an explicit expression for Sn. We keep this result in this formula. Now let's recap. An infinite geometric series is a sequence which is given by sums of increasing powers of some number q. Thanks to the calculation we just did before, we can get rid of the sum and rather write Sn as the explicit formula in the orange box. Now, our original question was, does Sn approach a limit or does it grow infinitely large? Now this translates to the question if this expression has a limit or grows infinitely large. In other words, we want to know if the sequence in the blue box has a limit or grows infinitely large. You see that the only thing that changes in these expressions is the power of q in the numerator. So everything depends on the question what happens with these expressions or this sequence when n goes to infinity. Now it's a fact that the sequence of powers of q converges to 0 whenever the absolute value of q is strictly smaller than 1. So from this follows that the sequence of these expressions tend to 0 if the absolute value of q is strictly smaller than 1. As a consequence, the geometric series Sn converges to g equals 1 over 1 minus q, whenever the absolute value of q is smaller than 1. To see this in more detail, we can write lim n to infinity of Sn equals lim n to infinity. Now 1 minus q to the power of n plus 1 divided by 1 minus q. This is nothing else than the expression for Sn we have found before. Now as q to the power of n plus 1 goes to 0 when n goes to infinity for all q such that the absolute value of q is strictly smaller than 1, we can write 1 over 1 minus q. So you see no lim anymore and also no q to the power of n plus 1 in the numerator anymore. So that is the limit. The limit of the geometric series whenever we have absolute value of q strictly smaller than 1. It is important to realize that this only works for these small q's, so absolute value of q strictly smaller than 1. For absolute values of q which are not strictly smaller than 1, that means which are equal to 1 or greater than 1, the series doesn't converge and the formula for the limit is not valid. Now with this in mind, let's get back to our series of the beginning. We had 1 plus 1/2 plus 1/4 plus 1 over 8 plus 1 over 16 and so on plus 1/2 to the power of n. And we ask ourselves, where does this go when n goes to infinity? Now we know that the so-called partial sums build a geometric series starting with 1 equals S0, 1 plus 1/2 equals S1, 1 plus 1/2 plus 1 over 4 equals S2, and so on. So the series Sn has the shape sum over the powers of 1/2. Now the exponent is I, and I is the summation index running from 0 to n. So that is a geometric series with q equals 1/2. Q is 1/2. Now obviously the absolute value of q is strictly smaller than 1. Consequently, we can apply our limit formula, so we know that the limit n to infinity of Sn equals, now the formula was 1 over 1 minus q. In our case q is 1/2, so we have 1 over 1 minus 1/2, and that is 1 over 1/2, which if we simplify that is exactly 2. So the sum of increasing powers of 1/2 has the limit 2 when n goes to infinity. Let's look at another example. We want to know what is the limit n to infinity of the sum over 1/3 to the power of I, and I runs from 0 to n. What is this limit? So this is also a geometric series which has the shape 1 plus 1/3 plus 1 over 9 plus 1 over 27 and so on with powers of 1/3. So where does this go when n goes to infinity? Now again, that is a geometric series with q equals 1/3, and again in this case we have obviously the absolute value of q is strictly smaller than 1. Now that means that we can apply our formula, and we know that the limit is 1 over 1 minus q with q equals 1/3, so we have 1 over 1 minus 1/3, which is 1 over 2/3, and if we simplify that we get 3 over 2, which is 1.5. So consequently, this sum converges to 1.5 when n goes to infinity. So let's summarize the basic finding of this video. Whenever we have a geometric series of the form I from 0 to n of some q to the power of n, we know that the limit n to infinity exists whenever we have that the absolute value of q is strictly smaller than 1, and that this limit has the value 1 over 1 minus q. So that's it for this video. Thanks for watching, and see you next time.